Hey everybody, and welcome back to Calc 3 Online. So I just wanted to quickly kind of pick up where I sort of left off in this problem, and I put the answers down in the last video, but really didn't have time to explain the answers. So I want to make sure I kind of take a little more time to do that, and then actually going to do another one of these because I think they're kind of tricky in this video. So so we did these pretty fully out, and I explained all these in the last video, but these were the last two that I hadn't done. And all these really, right, I'm just being lazy and putting, this in here. It's not like I'm truly integrating a 1. I'm just not writing the f of x, y, z every time. So if it really was a 1, right, it would be like a volume problem instead of like a hypervolume problem, but really this is like a hypervolume problem. So that doesn't matter though, because we're not really solving anything. I'm just being lazy. So for this part, we talked about too why it would always end in 0, 1, right? Because any of these projections, into the different planes here, always are capped from 0 to 1. So the end is always 0 to 1. That part for sure is good. We just need to figure out what it kind of looks like if we do like the dy first. And actually it'll be nice because whatever we put here for dy would also go here. Because again, if they start, like these two, this dx and this dx, you can go and just use the same bounds because it starts off the same way. Then later on it's going to change, right? But so if I was doing dy, right, I'm integrating from, basically from back here, whatever the, so this side, right, I'm integrating from there, like out to the, like in the, y direction here. So I'm going to end sort of my upper bound is right here. In y. I'm going, along that kind of y-axis, right? From the smaller y values out to the larger y values. And, if you just look at it, like what I literally just did, I said, we basically are going from square root of x, right, to 1 minus y. But 1 minus y, right, is also... you can't put 1 minus y, I guess is what I want to say, because you need it to be y equals something up here. So we need to like switch around the variables there. So if we add y over and then minus z, right, we would get that. So those are saying the same thing. So that purple side is 1 minus z. And you can use x and z in there because you've got x and z coming up later on right here. So I'm going to just go and put those in here because they are going to be the same bounds for that triple integral also. Then let's just, these are going to be different, right? Because this one starts off with x and this is z. So now they're going to change. So if I look at this one, a dx integral now, I think I might also, I'm going to clean some of this up. So for the dx, you can see that like, as I go in the x direction, I really start in the back there, like on that back triangular panel, right? And as I come out, well, just for that part, right, alone, you can see that you'll start at 0, right? You'll just, the x, the lowest value, is over here at 0, and we're going to come out towards this weird curvy shape here. So I'm going to just put in a 0. Because definitely we start at 0. And, it's coming out towards the y equals square root of x. So if I don't know what color I want. I'm going to do green. So if I can't use y equals square root of x because I can't put y in the problem anymore in the bounds because I did a dy integral. So, like, already it's kind of looking like x is y squared, but I can't use y squared, so I need another basically expression for y, and that's where this can come in. So I can use z because my last integral is a z. So, if I go back to kind of, I had it before, but if you think of this one as y equals 1 minus z, then I can literally just do substitution, put that in here, right? And, right, 1 minus z. And that is what I could use as a bound then for my upper x bound. So that'd be it for this integral, okay? Then we just got one more bound to deal with here. So I think once again, I'm actually gonna erase some of this. Okay, so this one, whatever your bounds are here, you want it to be at z equals, and you want the only variables in the bounds can be x, right? Whereas here you could have used z because we had z left over still. So I'm gonna go, I'm kind of looking at, the vertical sort of movement now, and you can see that you definitely do start over here at z equals 0. So we're going to go from 0 up to, let me get rid of that too, up to this plane, right? This like 1 minus y plane. But I can't use y because I can only use x. So you do the same kind of trick we just did before. You go, well, I want to use kind of 1 minus y. But 1 minus y, I can't use the y, so I take this, put it in here, and I would basically just do 1 minus square root of x. And so that would be okay to use. And 1 minus square root of x is, basically what we're getting for this upper part. That's kind of where we're ending right here. So that's it. So it's a lot of sort of just substitution, and these kind of things can definitely help you, I think, too. If I guess like even in the last one, I'm just thinking right here, if you look at this, right, we could also have gotten the answer this way because whatever bound you're going to put here can only have z and x. So if you look at z and x over here, right, you can see that you go in the z direction, you're going from 0 down here up to this curve. And this curve is 1 minus y, but then y is square root of x. So literally if you do, 1 minus square root of x, you're going to see this curve. And so that's why the upper bound. All right, so I just want to do one more of these, and they are pretty tricky, so I think it's good to cover a full another one. So it's literally the same kind of question. I just want to basically take, so this is one of the ways that you could integrate over this thing, but I want the 5 other triple integrals that basically work. And starting with dx, I think, is kind of tricky. So I'm going to start with the other ones here. So the 2 that go dx and then the rest of like the dA. Those are a little tricky. I'm going to save those for the end. So I'm going to do these other ones first. So I'm going to start off the same way here, where I kind of look at all the different projections. So here, let me fill this in. All right, so those are my 3 projections, right? One of them is really nice. If you just look at the, what is that one, the YZ one, there would literally be this square in the back, right? So, I'll just fill that one in really quick. That's going to be one of them. And the other ones, a little bit more work. You can kind of see them if you literally do just look in their corresponding planes. So this one, right, is some sort of like, curve based on the 1 minus x squared right there, right? That's in the x z1. And so here, we'll just call that one the blue one here. So we get this kind of curve that you can see over here, right? And that is the curve 1 minus x squared, right? Then you've got, we'll just do that yellow. You got this triangle down here, right? And that's in the xy1. And that is y equals 1 minus x. So those are my regions in the, 2D projections, kind of. And so let's start off. I'm going to do the same thing. I'm not going to bother writing the f of x, y, z every time. So I'm just going to write these three integrals down. So to do dy, you honestly could just steal it from here, right? But just so we kind of see it, you can see that we're going from 0 in the back, right, out to this shape right here, kind of, which is 1 minus x. So this part's not going to change, 0 to 1 minus x. Then for like the xz stuff, right, we could honestly just look here. We know that this is kind of what it looks like in the xz plane. And if you just, this is what z equals. So if z equals that, right, then if you solve, we need to solve for x because we're doing a dx here. So you can just rewrite that thing as an x equals. And you can see, right, I guess I should also say you go from 0 out to that blue curve. So you're going to go from 0 out to square root 1 minus z. So that would be the first one there. And then let's just do this one next. So for dz, right, you can see that we start down here at 0 and we're going to go up to this kind of curvy thing, this 1 minus x squared. So we go 0 up to 1 minus x squared, which also means that this one would start off the same way. And then this dy dx stuff is, over here. And so in dy, we go 0 up to the yellow line, 1 minus x. So we go 0 up to, 0 up to 1 minus x. And then this one will be pretty similar, except we're going to go 0 out right to, switch this around. It'd be 1 minus y. So 0 to 1 minus y. So those ones are fairly straightforward. The other ones are a little bit weirder. So if you look at doing dx first, the thing that's kind of weird is that you go, you're definitely going to go from 0. You're going to start from 0 on both, no matter what here. But what happens is, as you come out, right, in the x direction, you sometimes come out and you hit this thing as an upper bound in x, but you also sometimes hit this one as an upper bound in x, right? So, it's going to depend on kind of how high up you are. If you're like starting here, right, you're going to come out, that was bad to see. If you start here, you're going to come out and you're going to hit the green one, but like you could start like back there, and as you integrate out, you're going to hit the orange one. So the orange and the green are like both kind of upper bounds for this thing. So you actually kind of need to think of it in two cases. And that's why this one's a little trickier. All right, so for these other ones, they're definitely a little trickier. We're going to have to split them. And I think to start off, I'm going to draw this kind of two ways here. So, the weird thing is that basically in this back panel here, right, just looks like a big, square. But it's really built out of, this kind of is like a dividing line of that square if you project it back into there, right? So what I'm going to do is I'm basically going to imagine down here this split. So we have either kind of a part like this, or we're going to have a part like that. So those two regions together, I'm saying, will get you this square down here. And, this is in the YZ plane. And so the idea is like we'll do, we're basically going to do two integrals, two triple integrals to sum up and get the final, the final two remaining setups. So we're going to do one case here, one case here. And so let's just do we'll just kind of do it like this to save space. So they definitely all end in 0, 1 still. That's never going to change. 0, 1, 0, 1. And then we'll do this as the dx, dy, dz one. So I'm being lazy again. I'm not writing dx, dy, dz in here. But basically, let's do... the way I'll think about this is we kind of have like the minus x part, which... Here, I should keep my colors kind of good here. We got the minus x part. And then we'll have the x minus x squared part. So the minus x squared part I'm saying is, when this part projects back, we're getting that. And then the minus x part is, this part, the minus x part. When that projects back, we get this one. So those are the two triple integrals that I'm basically going to add together to get this full chunk, right? So I'm going to do this chunk plus this chunk. That's the idea. And I think I'm also going to run out of room here pretty quick, so I need to get rid of that. So on the minus x1, right, this curve would look like, y equals 1 minus x, but we can't use x, right? So we need to use like z or something, right? Because we used x. We can't have like the thing start off with like a y equals. So we just move that around. So it looks like x equals 1 minus y, right? So we go 0 to 1 minus y on that part. On the green part, right, to start off, we are kind of building off of this equation, right? And so again, you can't have x in that integral, so we just solve this thing for x. Let's see, if you add x squared over, then you get 1 minus z, so x is equal to square root of 1 minus z. So this part would start off 0 to square root 1 minus z. And then now, for these middle ones, I'm basically looking at the, I'm going to give myself a little more room there. I'm going to look at kind of the 2D projections, right? So I'm going to look at this projection for this integral, and then I'll look at this projection for this integral. And so for this one, you can see that we go from the curve, so in y, right, we're going, so this is y. Maybe I should, very crowded page here. This is the YZ plane, right, the YZ plane. And so I'm going from the curve, which is, built off of 1 minus x, but also this x equals square root 1 minus z. So I think I have to erase this too. But basically in the YZ plane, I'm doing y equals 1 minus x, but x is square root 1 minus z. So that's my curve that represents this, and I go out to 1, right? So this all has to get out of here. So on this chunk, I go curve 1 minus square root 1 minus z out to 1, right? Y equals both of those. And then on the green part, right, I actually start in y, I start at 0, and then I go out to the curve. And the curve is going to be defined basically, again, by just combining these two equations. So y would equal 1 minus x, but x is square root 1 minus z. So what's going to go up here is, I just don't have room in here. So at the star, you need it to be 1 minus square root, so 1 minus x, but x is square root 1 minus z. So that is the first case, right? Now the last integral would be just flipping this. But one thing that's nice is that now we have the first bounds and the last bounds, of course, would stay the same. So the only thing we basically need to change is the middle bounds, right? So I'm going to give myself a little more room here. All right, so I just deleted the part that wasn't really useful, because if we're splitting it anyways, this is really the projections that we need to be looking at for YZ. So filled in the 0, 1s, right? Filled in the first bounds, which are going to be the same as these bounds up here. And the only thing that's really different now is you just need to, you can't do like this integral as a y equals. It needs to be a z equals. And honestly, it's not too bad because we can just like flip around how we define it, right? So if we're doing dz in this part, right? So in the kind of right side of it, you can see that before we went from curve out right to here, now we're going to go bottom up to curve. So we're going to go from 0 up to this curve, and that curve was defined this way, right? So what we're basically just got to do is if y equals 1 minus square root 1 minus z, you just solve it for z. And if you do that out, you get z equals 1 minus y minus 1 squared. So that is basically what I would put in. So I'm going to do star. And star is 1 minus y minus 1 quantity squared. And then you do the same kind of trick here, right? Because, before we went from 0 out to the curve, but if we're doing dz, where we're going up and instead, we go curve up to 1, right? So we end at 1, but then we go from the curve up, and if you just do the curve rewritten, you're going to get the, it's honestly the same thing, I guess. So we'll just do, it'll be the same exact equation, right? So we'll just do star there too. So these two are the same. Whew. I always think these are hard, and they take a long time to kind of go through, especially to teach. But they really are important too, because there's lots of times where you just run into a function and it's just a bear to try to do it like dy, dz, dx or something. But it's like really easy maybe if you do z, x, y. So you need to be able to do this. And I won't make you suffer through this, but if you run into quadruple integrals, it's even harder, and you have to start thinking in like an even higher dimension. So I've done a few of those where I think in my life, like I remember them, where I've had to change orders of integration on like 4 integrals instead of 3, and you literally have to think in a dimension that we don't live in, which is really, really tough. And I'm not going to make you do that because I think it's really hard problem, but that is a thing that happens in math sometimes. So just know that that's kind of a possibility, but not something I would ever test you on. This one would even be considered hard, in my opinion, for something that would be a pretty tough question if I made you do this.